Now, on calculating quartiles, there's a handy-dandy little formula that what we first do is take all of our data and arrange it from low to high. So for our, say, a data set of 1, 5, 12, 15, and 20, 22, we would go ahead and arrange that from low to high. In this example, we've got 1, 2, 3, 4, 5, 6, 7 data points. And so n in this example can go all the way up to 7. Our I becomes our counter. We're arranging our data 1, 2, 3, 4. The I is simply the counter. So the first quartile is when I is equal to 1. 7 plus 1 is 8. And so we've got 9/4 comes on out to our data point. All right, welcome back to part 2 of the talk and looking at the variation. We're familiar with some of the words from before. So the standard deviation variance, we remember from our probability work that if something has a small standard deviation, it's going to be tightly packed around the average. And if we have a large standard deviation, that data is going to be spread out. Two other terms that pop in here for our measures of variation for our statistics, and that's the interquartile range. What's the difference between Q1 and Q3? Expressing that in terms of the actual data. And then finally, what's the difference from my largest data point to my smallest data point? That's known as the range, very susceptible to the outliers that are in our data. So gives us some idea of the largest, smallest, but one needs to be really, really careful with how you may use that actual data. So looking at this topic of interquartile range, as I had mentioned, the range is just looking at the data itself. What's the biggest minus what's the smallest, susceptible to both of those two values. The interquartile range gives you the middle 50% of the data, a little bit better indication because it's not a function of a single data point as the maximum minimum difference is, but it's rather the spread of the data itself. From the variance, the key things here is the use of Greek symbols for our population. And we have for our sample, we have Roman letters, in this case S squared being the equivalent of sigma squared. Notice as well, for our population variance, we're going to include every item in that population, and we go with little n minus 1. So if we have 10 data points, then that sample variance is going to be divided by 9. And we'll cover that a little bit later, not in today's talk, but where exactly that n minus 1 comes from as opposed to the total number actually in the population. So the standard deviation, nothing new there. We see the same n minus 1. This S is actually referred to as the sample standard deviation. When you use an Excel, you may want to be really careful. A lot of times you may think you're using population standard deviation, where if you look at the formula itself, it actually is down here as a sample standard deviation. So our distribution is going to have a shape associated with it. So if we look at the spread of data around its midpoint, and in this case we've got for symmetric data, the mean is actually equal to the median. So going back to our definitions, the average value is equal to the data point right in the middle. If something is right skewed, we've got a lot of data out here to the right, larger values of data. What that does is it shifts our mean from where it normally might be, where we think is it in the peak, and actually sliding it down. So for right skewed data, most of our data is over in this second half here. So it ends up that our mean is greater than our median. The opposite, similarly on the left skewed, the large number here of smaller data points is actually driving that mean down, and we have the case where the mean is less than the median for left skewed. We're going to see this in a little bit as a box and whisker chart as well to give an idea of visual representation. At this point, it's probably good to pause and actually look at the example 1 that was handed out for some sample statistics. So it's a data set here of 1, 2, 3, 4, 5, 6, 7, 8 points. So we know little n is equal to 8, and gone ahead and calculated the mean, median, and mode, which you can go ahead and double check, and the quartile measurements. So remember from our formula, Q1 is equal to 1 times n plus 1, in this case 8 plus 1, which gives us the value of 2. Remember, when we have our quartile data, we need to go ahead and rank order our data points so that we can begin to now, once we have the quartile number, to see what data point that actually aligns with, because that's really what we're interested in, not necessarily data point 2, but as we count down, what is that second data point? That's a value for Q1 equal to 4. Similarly, we go ahead and calculate Q3. In this case, we get data point 7. So go ahead back up to our data itself and look at data point 7 falls down at the value of 11. So Q3 is actually equal to 11. As far as the range, easy to do since we've already got it ranked up. So 22 minus 3 actually gives us our range of 19. The interquartile range is the difference between Q1 and Q4. In this case, we have a value of 7, and I know people are familiar with getting the variance and standard deviation. This data actually isn't reported as to what it is. Is it a population? Is it a sample? In that case, we're not really sure, so we can go ahead and calculate both values of the standard deviation. The population standard deviation of 5.8 and the sample standard deviation of 6.2. So there's a walk through the worksheet and some use of those vocabulary words. And our next topic is actually now looking at the topic of statistics and see how they're tied to normal distributions.